Hello and welcome to Engineering Economy. This is Dr. Ala Kamerdiner. We will talk today about uncertainty in future events. The outline for today is single estimate versus a range of estimates, probability distributions in economic analysis, and expected value and economic decision trees, and last but not least, risk versus return. We will also briefly discuss simulation in economic analysis. So the learning objectives for today is we will be able to use a range of estimates to evaluate a project. We will describe possible outcomes with probability distributions. And we will combine probability distributions for individual variables into a joint probability distribution. And we will use expected values for economic decision making, and we will use economic decision trees to describe and solve more complex problems. We will also measure and consider risk when making economic decisions. And last but not least, we will understand how simulation can be used to evaluate economic decisions. So let's discuss this interesting example. They only thought they were done. Superfund. The federal law requires companies to clean up property sites that are contaminated by hazardous waste. Hundreds of sites have been cleaned up at billions of dollars. A large number of Superfund sites have been found to contain TCE, a widely used solvent. Environmental Protection Agency discovered that TCE may be far more toxic than originally thought. And so the cleanup techniques used in the past to remove this solvent and this toxin have made the problem worse. EPA is studying whether previously cleaned sites should be reopened for additional remediation of TCE. How can a company quantify the risk of an event such as discovery of TCE on its property? What are some ways a company might estimate the cost of such an event should it occur? Prior to mid-1970s, it was common and legal for manufacturers to landfill chemical and other potentially hazardous materials. When Superfund was adopted in 1980, it required companies to clean up the landfill. How can companies anticipate and prepare for future laws that might penalize activities which are legal today but may become illegal in the future? So when you think about it, a natural thing that comes to mind is uncertainty in future events. And when you talk about estimates in economic analysis, we of course need to be able to evaluate future consequences of an alternative in order to perform economic analysis. And usually a single value is selected to represent the best estimate that can be made. Economic analysis was conducted assuming these estimates were correct. In Chapter 10, we also talked about doing a sensitivity analysis when we might think, okay, what if our estimates weren't really quite correct, and what if we can adjust them? However, we also want to understand not only the impact of estimates on economic analysis, but also trying to understand what are different scenarios or what are different situations that could potentially be realized. So here's an impact of estimates in economic analysis. We have two alternatives, A and B. They have initial cost. Here's their initial cost. They have annual benefits. They have the same useful life in years, 10 years. And then they have end of useful life salvage value. So let's say an alternative A has $100 of salvage value at the end of useful life, and B, we estimated to have a salvage value of 400. And what if we are wrong, and rather than having the salvage of 400 in the future, we only will get 300 rather than 400? So let's first take a look at net present worth of A. So again, very simple. This is initial cost, so it's in the present, so it's already present. We have a negative because it's a cost. Then we have the annual benefit, so it's annual amount. We need to find its present equivalent. So this 150, which is annual amount, we need to find its P equivalent. So PA, the same order, we have discount factor PA, and then 3.5 is our interest rate here, and then we have 10 years, so 10 times each year we have those annual benefits, so we have 10 here. And then at the end of 10 years, we have the single value, which is salvage value. That's actually a future with respect to the beginning of the project. So that's at the end of 10 years. So that's a future amount. And so this is 100 is of F. We want to find its P equivalent, or present worth equivalent. So P, F, the same discount factor, the same order P, F, P given F, 3.5%, 10 years. So when we plug in the values for P given A and P given F and evaluate this expression, we get 319 as a net present worth of alternative A. Now we can do similar computation for B, assuming all of these values with a salvage value of 400. And in fact, right, this is very similar. The only difference is actually using a different values, but it's very similar, analogous, basically how we compute the net present worth of B to how we computed net present worth of A. So after we evaluate the expression, we get 363. So of course we want to maximize the net present worth. And so when we look at this from the standpoint of maximizing net present worth, then we see that 363 is larger as 319, and so we would prefer B. Well, what if our estimate of this future benefit salvage value at the end of 10 years was incorrect? So rather than having 400, what actually is going to happen is that we're going to only get 300 out of it at the end of useful life. What if that happens? Well, we can compute it using this different estimate, and what we see is actually we're going to get, again, the same way as we computed before. The only difference is here we're using 300 rather than 400 because this is a better estimate. So then when we do that, what happens is that we get net present worth of B is 292, which is less than 319, which was the net present worth of A. Then if we were comparing 319 and 292, the 319 is higher, it's bigger, so maximizing the net present worth, we would choose A instead of B if 300 is a correct estimate. So you can see that there's a potentially a big impact on a decision here in this case. So now let's take a look at this example. So what we can do is we can use break-even analysis in dealing with the variability in the estimates. And that also have been discussed in chapter 9. So here in this case, we have two projects again, A and B, and the same or similar, the same for project A, the same values as we had before, and again the same values for B, except that here this salvage value is an unknown. So we want to know, right, when these two projects are equivalent. So when do we break even? So to do that, we're going to set up the equations of net present worth. For A, we already computed it to be 319. For B, we're gonna write it out and have the X here instead of 300 or 400, but the rest is basically the same as in the previous example. So then, to find the break-even, we set these two to be equal, or if you wanted alternative B to be selected, then we're setting the equation to be net present worth of B should be more equal than net present worth of A. So when we do that, then again, right, what we can do is simplify this a little bit so we can evaluate P given A, right? This is a number. So when we evaluated the negative 2,000 plus 250 multiplied by this value of this discount factor, then that simplifies to 79. So we'll actually get 79, and then this P given F, this value is actually 0.7089. That's the value of this P given F here. So this simplifies, right, this net present worth equation, this simplifies to 79 plus 0.789x. And so this should be more than 319, which is the net present worth of A, for alternative B to be selected. And so when we solve for x, we get x should be more or equal 339. So as long as x is more than 339, we'll select alternative B. But if it's less, then we would select alternative A. And graphically, we can represent this as follows. Alright, so this linear trend right here, this line here, is actually the net present worth of B. It's basically 79 plus this 0.7089x. And then 319 is this horizontal line is 319. And so you see that this is where they intersect. And that's break-even point, that's 339. Alright, so let's talk about why we would want to use a range of estimates in economic analysis. Rather than looking at break-even analysis, it's more realistic to describe parameters with a range of possible values, rather just in any single value. And this range of possible values, it could include, for example, optimistic estimate, the most likely estimate, and a pessimistic estimate. So we're going to denote them optimistic O, most likely M, and pessimistic P. So then you could use a beta distribution with the approximate mean value of parameters that can be calculated using this formula. It's the optimistic plus the pessimistic plus 4 times most likely divided by 6. So let's take a look at this example. So we have optimistic, most likely, and pessimistic cases. We have, for each of the cases, we have initial cost, net, annual benefit, useful life in years, and salvage value. So what we can do is we can use this beta distribution to find the mean values, and we could also find the net present, actually the rate of return for different cases. So if we take a look at the optimistic case first, in order to find the rate of return that we get in this optimistic case, we need to set net present worth of it to 0. So to compute the net present worth, we take this is initial cost, so it's already in the present, and it's a cost, so it's gonna have a negative, so this is negative 950, and then net annual benefit is positive, but it's annual, it's not a P, not present, so we're gonna turn it into its present equivalent. So P and this 210 is A, annual benefit A, so PA, and in the same order we have discount factor, PA, I and 12, where this I that we will determine is going to tell us the rate of return. And then of course we have salvage value, and that's a future value. So we want to find its present worth equivalent, so P given this F. In the same order we have discount factor P, F, I, 12, right, because its useful life is 12. So then if you were to solve this equation and find the I that satisfies it, we will get about 19.8%. So that's the rate of return for the optimistic case. We can also do the same for most likely and pessimistic. So for most likely, using similar way, we're computing it by using these values. We get 15.1%, and for pessimistic, we get 3.9%. So you see this internal rates of return. So now we can also use the beta distribution. So using the beta distribution, we can find mean values. We can find the mean value of the cost. We can find the mean value of net annual benefit, a useful life, and the salvage value. Right. So again, then we can set up the equation net present worth equals to 0. Again, similar way. This is the already present. This is the annual, therefore we multiply it by P given A, and this is the future amount, so we multiply it by P given F. So again, the useful life is 10, so that's what we're using here in both cases. So from this equation, setting it up to 0 and determining the I that satisfies this equation, we get this value of internal rate of return, and that's 14.2. So that's internal rate of return for mean estimates. So now let's take a look at concept of probability. So you might have already heard of probability, because it's a useful concept that is being applied to many different disciplines. So what is a probability? A probability is the likelihood of an event in a single trial. So if we had, for example, right, if we tossed a coin and it's a fair coin, then the probability of getting a head is 1/2, or a probability of getting a tail is also 1/2. So it also describes this probability. It also describes the long-run relative frequency of outcomes occurrence in many trials. And probability has some very strict rules. Specifically, the probability is the value of probability is always between 0 and 1, including those. And the sum of all outcomes for these all possible disjoint outcomes is 1. So this big sigma sign, it actually denotes the summation. So if you were to sum P outcome 1 plus probability of outcome 2 plus probability of outcome 3 and so on, plus probability of outcome K minus 1 plus probability of outcome K, that would be equal to 1, right? So this is just a summation. So now we have different distributions. We often talk about continuous and discrete distributions. So some common continuous distributions are normal, continuous uniform, exponential, and weighable. There is also, like I said, discrete distributions, and the common discrete distributions are binomial, discrete uniform, geometric, hypergeometric, Poisson, and we can come up with some custom distributions as well that are discrete. So now let's take a look at this example. So again, we have our optimistic, most likely, and pessimistic cases for annual benefit. If it's optimistic case, then we have annual benefit of 10,000. Most likely we would just get 8,000, and in a pessimistic case we only get 5,000. And so the probability of 10,000 needs to be determined, but we know that most likely it happens 60% of the times, and pessimistic situation happens 30% of the times. So these percentages means that the probabilities are actually, this corresponds to 0.6, which is exactly between 0 and 1. And this corresponds to 0.3, which is exactly between 0 and 1. So that's regarding annual benefit. Now, separately from the annual benefit, we also have life and a distribution for the life. So these are two different distributions. One for annual benefit, which has optimistic, most likely, pessimistic. For life, we only have two situations. For annual benefit, we have three. Optimistic is first, most likely is second, and pessimistic is third. But for life, we only have two situations. It could be life of 9 years, or it could be 6 years. And so probability, we know that probability of 9 is unknown, but we do know that probability of having a 6-year life is twice as likely, right? So it's twice as likely that we get the life of 6 years rather than the life of 9 years. And so from just this, we can find the probability of 10,000, and we can also find the probability of 9 years and probability of having a life of 6 years. So what do? We, in this case, we use this summation, right? So summation of all, that's the rule that says that summation of all possible outcomes should sum to 1. So here the possible outcome is 10,000, 8,000, or 5,000. So if we add all of these probabilities together, they should sum to 1. Right now we have 0.6 and 0.3. These sum to 0.9. So then subtracting that from 1, we get the probability of 10,000 is 0.1 or 10%. And that's exactly what you see, right? Probability of 10, so that we're going to have this 10,000 optimistic annual benefit is 1 minus the other ones, right? Using this rule that all the different summation of all different of probabilities of all different outcomes should come to 1. So now this is just a representation, right? Representation of how likely things are. You can see that most likely case is in fact most likely, right? We have 60% chance of getting the 8,000 benefit, 30% of 5,000, and 10% chance of 10,000. So then, if we wanted to find the probability of having life of 9 years and probability of having life of 6 years, we'd also, right, add the probabilities using this rule, add the probabilities P9 plus P6 and say P9 plus P6 is 1. So using this, P9 plus P6 is 1, because P6 is twice P9, and so you're plugging in twice P9 here, we get P9 plus twice P9, so it's 3 times P9 equals to 1, so divide both sides by 3, we're gonna get P9 is 1/3, and therefore plugging this in here, we get P6 is 2/3. So we found out that P9 is 1/3 and P6 is 2/3. So now let's talk about joint probability distributions, because we have two different variables. We have annual benefit and we have useful life. So a joint probability distribution is needed to describe the likelihood of outcomes that combine two or more random variables, and each random variable has its own probability distribution. If events A and B are independent, the joint probability for both A and B to occur is just the product of PA and PB. But that's only true if A and B are independent events. So now let's take a look at this example. So here what we assume that annual benefit is independent of the life. So we have corresponding probabilities for benefits. right? For 5,000 it's 0.3 here and also here. For 8,000 it's 0.6 here and also here. And then for 10,000 it's 0.1 here and also here. And then we also look at, okay, if we have 5,000 annual benefit, we could have life 6, or for 5,000 annual benefit, we could have 9. So for any different value of annual benefit, we could have either 6, life being either 6 or 9. And these are probabilities for the life, right? The life, the probability of life being 6 years is 2/3, so approximately 0.67. While probability of life being 9 years is 1/3, which is approximately 33%. So now we can get the net present force for each of the event, right? And here we also including not only annual benefits in using the number as a life. We using specific I interest rate, and we also using a initial cost. So I'm not telling you what it is here. You can look it up in the textbook. That's example 10.6. But here we can compute net present force. And then we can also look at the joint probability, right? So the joint probability, this is 0.3. We assume benefit independent of life. This probability of benefit, this probability of life. So we can multiply them together because we assume that benefit is independent of life. So we multiply 0.3 by 2/3, right? Because this is actually 2/3. So the 3's cancel out. This is going to be 0.2. And so on for the rest of them, right? Here 0.6, and this is 2/3. So again, this is going to be 0.4, and we can compute all of these joint probabilities simply by multiplying this probability in this probability, right? So we just cross multiplying these columns, and we get this column of joint probability. And this net present force is based on the life and the benefit, and also the initial cost and the interest rate. Alright, so now that we computed the net present force and the joint probabilities for each of those net present force, we can represent these, right? So you can see this negative 3,224, that's for annual benefit of 5,000 in a life of 6 years. For that we have 20% likelihood, right? So 20% probability of this to happen. And then for this 9.842 net present force, we have 0.4 joint probability, so you see that 40% here, and so on. This is just a graphical representation of the net present force and its distribution. So let's discuss let's talk about the expected value. And so you might have already heard about expected value, so I wanted to once again to kind of explain what it is. And an expected value of a probability distribution is simply every weighted average of all possible outcomes that's weighted by the probabilities. So that's a formula where we have, right, just a cross product of outcome by its own probability. So we have the sum of these products of each outcome by its probabilities. And to make this clear, let's take a look at this example. So here we have the optimistic case again, most likely, pessimistic in terms of benefit, and we have the different lives in years. So it's kind of a continuation of the previous example. So now we can find expected value of the benefit. And so notice what we're doing is we just multiplying to find the expected value of benefit. We multiplying this by this by this, and this by this, and sum them together. And that gives us 7,300 as expected value of the benefit. And similarly, we're going to do the same for years and get the expected life. So we just multiply 9 by 1/3 and 6 by 2/3 and add those products together, and that gives us expected value of life. and that evaluates to 7. So now that we have the expected value of benefit and expected value of life, we want to find the net present worth of expected values. So the net present worth of expected values, notice that net present worth of expected values is not going to be always the same as expected net present worth. Right? They're not necessarily the same. So net present worth of expected values, we using the right, so this is our initial cost, 25,000. In this example, we have 10% interest rate, and then we're using this expected value of benefit here, and so adding that together, right, using the 7 as expected value of life, and we're gonna get this much as net present worth of expected values. So now let's take a look at the example where we again look at joint probability distributions. So we have annual benefits and then their respective probabilities, and we have different lives and their respective probabilities. And so that allows us to set up, as we did before, the present worth for each example, right? For this row, we get this present worth. For this row, we get this present worth, and so on. And then for this row, we have this joint probability, simply by multiplying 3 by 2/3. For this row, we get this joint probability, multiplying this by this, and so on, right? So this is what we did before. So now, what we can do is we can find, knowing the net present worth for different situations or outcomes, and knowing the joint probability, we can also find the expected present worth, right, or expected net present worth. And that's done by simply cross-multiplying the present worth by its corresponding probabilities, and then summing those products together. So we're first multiplying those, so this multiplied by this, we're gonna get this much. This multiplied by this, we're gonna get this much, and so on. So then, what we're gonna do is, this is the products, we're gonna sum those products together to get the expected value. So expected value of present worth is gonna be this much. So notice 10,000 and 209 is expected worth of present value. That's different from what we had here as net present worth of expected values. That's 10,536. 10,536 is not the same as this 10,209. So you can see that net present worth of expected values is not the same as expected value of present worth. So now let's take a look at this example. Here we have different dams, and we have their initial first cost, we have their probability of flood, that's annual probability, and also the amount of damage if flood occurs. So now we can find the equivalent uniform annual cost, and simply by multiplying the initial cost by a factor A given P, and we expect the dam to last 50 years, and we use the minimum attractive rate of return of 5%. So we use interest rate of 5%. So that gives us the equivalent uniform annual cost based on the first cost. So of course, if we have no dam, then it just would be 0. For 20 feet dam, we would use 700,000 here instead of I. And then for 30,000 dam, for 30 feet dam, we would use 800,000 as this I here to find the equivalent uniform annual cost, and so on. Also for 40 feet, we'll use this value. So that will allow us also to compute the expected value of annual damage, which is basically it's a damage that occurs, and then multiplied by the probability of the flood. So the annual probability of flood is, in the case when there's no dam, it's very high, it's 0.25. And so notice, right, these are separate situations. They're not, different outcomes, right? Because if we have no dam, that excludes the possibility of 20 feet dam. So these are not the outcomes. These are different situations. So again, this is conditional on specific dam. So given there's no dam, then we have probability of flood being 0.25. And then this is the amount of damage that happens if we have the flood. And so for different height of a dam, we have different flood damages, which is decreasing with the height of a dam being higher. So then we can find, as I said, the expected value of annual damage simply by multiplying the damage by the probability of the flood. And so this is what we're gonna get, right, for different dam height. The equivalent uniform annual cost of this first cost here is simply, right, 0 multiplied here in this case by this A given P, so it's going to still be 0, and then 7,000 multiplied by A given P value is going to be this much, and so on. And then expected annual flood damage is simply this 0.25 or 1/4 multiplied by 800,000, so that simplifies to 200,000, and that's what you see here, and so on. This is 0.05 multiplied by 500,000 is going to be 25,000, and then the 0.01 multiplied by 300,000 is going to be 3,000, and then 0.002 multiplied by 200,000 is going to be 400. So then we can get the total expected annual equivalent uniform annual cost, and that's basically including the equivalent uniform annual cost of first cost and an expected flood damage. So we're just adding those because this is already annualized. We annualize the first cost, and this is already annual. So the cost plus the damage is going to be 200,000, and that's what we have in terms of total expected uniform annual cost when we have no dam. And then for 20 feet, we add this, which is annual equivalent of first cost, plus the expected annual flood damage. Adding these together, we're going to get 63,000, and then adding these two together, we're going to get 46,000, and then adding these two together, we're going to get 49,000. So you can see, right, we're going to try to minimize the cost, because this is a cost. We're minimizing total expected annual equivalent uniform annual cost. And you can see that the smallest value is 46,821. So that corresponds to the dam having a height of 30 feet. So that's what we're going to choose. We're going to choose the alternative of building a dam that's 30 feet high. And in that case, we minimizing our expected annual cost. So now let's take a look at economic decision trees, and these are really useful when you have some complex situations. And they allow us to graphically represent all decisions in a complex project and all the possible outcomes with their probabilities. And we have a decision node. This is how we denote the decision nodes in this type of figure here. And then for each decision node, we also specify the decision, right? So we have X different decisions, D1, D2, Dx. We also have the chance nodes. So the chance nodes are ovals, and in addition to the description of what kind of chance or what kind of outcomes happen, we also have the corresponding probabilities. Notice for decisions, we don't have the probabilities because we only going to select one decision. We're in control of it. We're not in control of chance. We just represent all different possibilities that could potentially happen. And then we have an outcome node. An outcome node is basically, right, as what's going to happen. There's a square here, or rectangle, more like rectangle. And then we have prune branches. Prune branches mean the branches, right, that we eliminated. For example, in a decision, right, we can't really eliminate chance nodes because we don't have control over chance nodes or uncertainty. We don't have control over uncertainty. But we have control over our decisions. So if, say, decision 2 is worse than decision 1, then we will definitely eliminate decision 2. We say, well, we're not going to select D2 because we would do much better making decision D1. And so then we would prune this branch that leads to D2. And why is it useful is because this is, the tree has a bunch of different nodes. So this might be one decision, but there might be additional decisions. So pruning the branch eliminates whatever is in after it. So here's an example of a decision tree. We build a new product in time 0. We can either decide to build it or not build it. So if we don't build the new product, we get a revenue of 0. If we do build, then we're gonna incur the first cost of 1 million. And then we don't really know what's gonna happen, but we might have some type of volume for new product in terms of what's gonna be demand for our product. So demand could be either low, medium, or high, right? We could have really low demand for our product, medium demand, or high demand. And this is a chance node, right? That was a decision node. We were in control of this. This is a chance node. We're not in control of it, but we know how likely different chances, different outcome, right? So low volume happens 3% of the time, medium volume is 60% likely, and high volume is 10% likely. So then if we have a low volume in year 1, that's the amount of revenue we get in year 1. We get 100,000. And so that's our decision node, right? So we get this revenue, we could either continue or if we can terminate. If we terminate, then we're not gonna do much. It's just gonna give us a net revenue of 0 after this. And then if we continue, we're gonna keep accruing this benefit or getting this benefit of 10,000 each year. Then for medium volume, we also have a decision. Well, actually, we just have an outcome. If we have a medium volume, we're just gonna continue and keep getting 2,000 in year 1, and in consecutive years 2 through n, we get also 200,000 as net revenue. But for high volume, we also have a decision to make. So we can either continue, right? We get the net revenue in year 1 is high because of the high volume is going to be 400,000, and so we have to make a decision whether we're gonna just continue at this level or if we're gonna expand in new markets. So if we expand, there's additional cost associating with reaching new markets. For example, like advertising cost for our product. So that's 800,000, and what's gonna happen in terms of outcome is we're gonna get even higher revenue, rather than just 400,000, we're gonna get 600,000 per year when we expand. But then we could also just continue rather than expanding, and that would continue keep giving us 400,000 in consecutive years. So we'll get a net revenue of 400,000 per year. So as you can see, we have this kind of tree, right? It's called the tree because, right, not only we have a graphical representation, but you can see it's kind of almost has this kind of branch type of representation, right? Where we have the branch here, then it branches off in different branches, so it almost reminds a tree. And so these outcomes here are for years from 2 to infinity. So based on this economic decision tree, what we want to do is we want to select the decisions. So again, we're looking at this tree, and usually we're going to start working backward. So we continue, we had this tree written out. What we're going to do is we're going to then find the net present worth for this. So the present worth for this node is going to be 550,000, and that's again just based on year 1, and then discounting it back. And then if you have this revenue, then we're gonna get present worth in year 1 is gonna be 486,080. So comparing these two, right, we can make a decision either terminate or continue. You can see that present worth here is smaller than right here, so we're gonna terminate. Terminate is gonna save us the cost. So this is the revenue, but it doesn't include the cost. So based on the cost, we better off just terminating because it gives us a larger present worth, right? If we continue at 1,000 a year, it looks like we're not gonna do as well as we would if we just terminated. Then we wouldn't have the cost, and the revenue would be 0. So now we can prune this branch, so we're not going to continue in this case if we get the low volume. And then working back, incorporating this, working back, we get the present worth. So that's at time 1, present worth at time 1. This is present worth at time 0. So we got this value. And then here we're going to get the revenue for year 1 through 8, so only for 8 years. The life is going to be 8 years, and that's going to be 200,000. So incorporating these revenues from year 1 through year 8 at given interest rate, we'll get present worth value of 1,067,000. And then here we need to check and compare expanding to continuing the option, right? So if we computed this expanding option, that's how much we're gonna have in terms of present worth in year 1 with respect to year 1. So before we incur this first cost, we're just looking at this first cost here, versus here we don't have any first cost, but we also have a lower revenue, and that goes to infinity. So this is our present worth of 1 for 2 different options. So you can see this is actually under 2 million, and this is over 2 million, so this is higher. So we select this one and prune the continue branch. So now if we get the high volume, we're gonna definitely expand, and so we're gonna go back and compute the present worth. So that's the present worth for this, situation for high volume. So now we have present worst for low volume, present worst for medium volume, and present worst for high volume. And we have their probabilities. So multiplying this probability by the corresponding present worst, and then multiplying this present worst by the corresponding probability, and multiplying this present worst by its corresponding probability, and then summing those together, we're gonna get expected value here. So expected value is gonna evaluate to this much, and that's when we also take into account this first cost of $1 million. And so this rate is still better than 0, and therefore we're pruning this branch. And so again, if you were to look at a little simpler example of using economic decision tree, we could have two options. We could buy insurance or self-insure. If you buy insurance, we have to pay $800. If you self-insure, you don't pay anything. We have chances, different chances when we buy insurance, and when we self-insure, we pretty much have this similar situations happening. We could have an accident, either a major or minor accident, or we don't have an accident. So no accident is 0.9%, small accident is 0.07, and we can total our car, and that has a probability of 0.03. So again, these are coming out of Ch10's notes, so we cannot prune these branches. However, we can find, and the same again for self-insurers, the same exact thing, we can find the expected values, right? So if there's no accident, we're not gonna pay anything. If there's a small accident, we're gonna pay $300 because what it costs us to fix things are less than our $500 deductible. And if we have the car totaled, then we just pay the deductible of $500,000, and the rest, the insurance company picks up for us. If you self-insure, on the other hand, when there's no accident, we're still gonna pay only 0. And so here you can see we can find the expected value simply by multiplying. So 0 multiplied by 0.9 is going to be 0. Then $300 multiplied by 0.07 is going to be 21, and then 500 multiplied by 0.03 is going to be 15. So 21 and 15 and 0 is going to be 36. So now that we have the 36 expected value for buying insurance, we also want to do the same for self-insuring. So no accident, we still have 0. If it's a small accident, we're gonna pay 300. That's how much it costs to fix it. And then if it's total, we have to buy the new car out of pocket. So that's costs us $13,000. So then we again multiply these by their corresponding probabilities. So 0 by 0.9 is going to be 0. 0.07 by 300 is going to be $21. And then 0.03 multiplied by 13,000 is going to be 390. So we're going to get 390 plus 21, so that's going to be 411, and that's exactly the values that we get here, expected value. So when we compare it, right, the buying insurance, right, we have 36, but we also add 800. So together, that's going to be 836 versus self-insurer, we pay 0. So 0 plus 411 is going to be 411. So we're actually comparing 836 with the 411. And so you can see that 411 is less than 836. Right? 800, because when we buy insurance, we need to add that to the expected value. So we're going to prune this branch of buying insurance and go with self-insured. right? Of course, that's when we minimize or when we look at the expectation as our criteria. So expected values are only one of the criteria. The other criteria is risk. And the risk can be thought of as a chance of getting an outcome that's other than the expected value. So there are many measures of risk, including probability of a loss, and you can see example 10.6 if you wanted to learn more about that. And we have standard deviation as a measure of risk, and the way it's computed is just using this formula, right? And there's an alternative formula that could also be used, and this is how we can rewrite this just using the definition of expectation. So now here's an example, and that's continuing the example 10.11, but calculating the risk for this self-insuring versus the buying insurance. So the expected value is, right, we calculated, and is the expected value squares, right? So if using that formula, the second formula, we also want the expected value as expected of value squared. So expectation of value squared is here. We have 0 squared, 300 squared, and 500 squared multiplied by the respective probabilities. So that's evaluates to 13,800 for buying the insurance, and for self-insuring, again, the same way. We're finding the expectation of value squared. So square this, and square this 13,000, and we get this much, right, which is more than 5 million. And so then we can find the risk of buying insurance. That's expectation of value squared minus the square of expected values, and the same or not the same but similar formula we're using here for self-insuring. Plugging in the values, we get that buying insurance, right, is gonna have this risk of $112 versus self-insuring. The risk is going to be much higher. It's going to be 2,215. So again, if we were risk averse, we would try to minimize the risk, and the smaller one in this case is to buy insurance because it has a smaller sigma or standard deviation, so we have smaller risk. So you can see, depending on which measure we use, we're going to have a different decision, right? When we just used expectation, we came to the decision to self-insure, but when we're looking at the measure of minimizing the risk, then the buying insurance is the option. So again, here's another example, and that's the examples that we looked at where we have three different annual benefits. Pessimistic, most likely optimistic case with the respective probabilities, and then two different situations in terms of life of years, either 6 or 9. So we can also compute risk. So again, we already did this. That's just from before, the net present force, the corresponding joint probabilities. Then we multiply each of these together, this by this one by this one by this one, to get these values in this column. And then summing those together, we got the expected value of net present worth. So then we can also do this for squared present worth. So when we square this negative 3,000, it becomes positive. So now this is positive here too. So this is squared and then multiplied by their joint probability. Again, this is squared multiplied by joint probability, that gives us this. So we can do all those cross products of squares with the joint probabilities and then sum those up, and that gives us the expected value of squared net present worth. So then we can compute risk simply by, this is going to be square root of this minus this whole thing squared. That's like what we have, right? So we're plugging this in, this is squared, this is from here, and then finding this out, taking square root, and it gives us a risk estimate of 9,229. as written right here. So then let's take a look at the example of risk versus returns. So we have different projects, right? Project 1, 2, 3, 4, 5, 6, 7, 8, and F. And we have the respective rate of returns and then the standard deviation of this returns, right? So this is expected return. This is the standard deviation of returns. So how do we look at it? Well, if we were just to maximize, right, the return, then we probably choose project 6. However, project 6 still has a pretty high standard deviation. And so in reality, what we actually would do is we would look at expected value of return versus the standard deviation of return, right? Because this would be, we would want to maximize the expected return and minimize the risk. And so this is the risk measure. So what we want to do is we want to be somewhere up above here, and so the F alternatives, the 3, 2, 7, and 6 are better ones than the ones that are below here, right? For example, if we take 4 and we wanted to right, so it's a multi-objective optimizations that we're looking at here. So if we had 4, the two criteria are, we want the smaller standard deviation. We could achieve it selecting 3, right? Selecting 3, we're gonna get smaller standard deviation with a higher expected value than 4. If we were to look at 4 and say, well, we want the higher expected rate with a smaller standard deviation, then this 3 is way better. And the same for 1, right? We could reduce, right, the standard deviation, for example, or we can increase the expected value. So again, 1 is not a good option, and similar goes for 8 and 5. So these are projects, these 4, 1, 5, and 8. These projects are not as good as these projects F, 3, 2, 7, and 6. And overall, like as you can see, there's a trade-off between the risk and the return. So now, last but not least, I wanted to discuss the simulation. Of course, the trees that we saw, even that big trees that we draw, where we looked at different products and high, low, and medium volume of the products, that was a small, relatively small tree. However, when we have multiple chance nodes, multiple decision nodes, maybe different time periods, that whole computation becomes very tedious, and therefore a simulation would be more suitable, where we can really, if the tree becomes really, really large, it would take us too long, prohibitively long time to explore all the branches. So the simulation allows us to just select a few representative branches, and so that's an advanced approach for considering risk in engineering economic analysis, and it uses this random sampling. So rather than considering the whole, all different possibilities and all the branches in the tree, we're looking at just randomly picking from the probability distributions of one or more variables to analyze the economic model for many iterations. And for each iteration, all variables with probability distribution are randomly sampled, and these values are used to calculate net present worth, internal rate of return, and equivalent uniform annual worth. And the results of all iterations are then combined to create the probability distribution for net present worth, rate of return, and annual worth. And simulation can be performed by hand with a table of random numbers, or by using Excel functions or standalone simulation programs such as @RISK and Crystal Ball. So that basically is where we want to add. This is all we have for this topic. And just one thing that I wanted to mention, since we talked that this whole computation is kind of tedious, is what we can use as a help in terms of numerically doing numerical calculations for the simulations. So in Excel, for example, we have this rand function, and the rand function, it returns an evenly distributed random real number greater than or equal to 0 and less than 1. And a new real random number is returned every time the worksheet is calculated. And then for norm_inv, it returns the inverse of normal cumulative distribution for the specified mean and standard deviation. So these two functions are particularly helpful, and here's an example from 10.5 where you can use the Excel functions. So here we assume this annual benefit of 250 per year, and we have some initial cost. It's assumed normally distributed with mean of 1500 and standard deviation of 150, and useful life is uniformly distributed over 12, 13, 14, 15, and 16 years. So what's interesting here is that we could actually take advantage of some of these functions that we talked about to get the initial cost generated and the useful life generated. So the Excel equations for life would be 12 plus this int multiply or int of rand multiplied by 5. So why do we do that? Well, if you look at rand generates a random number between 0 and 1. So when we multiply it by 5, it basically will generate a random number from uniform continuous distribution between 0 and 5 rather than 0 and 1. And then when we take the integer part of it, it's almost like dividing this values, right? It's between 0 and 5. So if it's less than 1, then we can get 0. If it's less than 2, if it's more equals than 1 but less than 2, we're gonna get a 1 here. If it's more equals than 2 but less than 3, we're gonna get 3 here for this whole thing. And then if whatever we generated was a rand multiplied by 5 is less than 5 but more equals than 4, we're gonna get 4. And so there's only 4 different actually 5 different things: 0, 1, 2, 3, 4. So 5 different things, and then we adding 12, so 12 plus 0 is going to be 12 years, 12 plus 1 is going to be 13 years, 12 plus 2 is going to be, 12 plus 2 is going to be 14, 12 plus 3 is going to be 15, and 12 plus 4 is going to be 16 years. So that's how the life is generated. But then, of course, we also have this initial cost. And we know how to generate uniform, but then if we have an inverse, we could plug the seed for the normal inverse, and then get the normally distributed values. So here, right, this is the mean, this is the 150 in terms of the standard deviation, and the rand is generating this uniform seed or uniform the x value. So then it says gives us the normally distributed initial cost. And then of course we could find the rate of return by using the rate function. And then we just plug in the rate, we plug the whatever we got the life, in whatever cell we have this equation for the life. 250 is our annual benefit, and then whatever the initial cost we have here. So again, this just represents, this representation gives us internal rate of returns, right, and this is the frequency of it. So that's just an example of how we can compute the rate of return for this situation. Alright, so that concludes my presentation of uncertainty and how to deal with uncertainty in engineering economic analysis. I hope this is useful, and in particular I really believe that it could be really easily extended, right? This example can be really easily extended for understanding the randomness in the game. Remember, in our economic decision game, we have pirate ships and we have the fishing ships, fishing vessels. So we could use these formulas. For example, right, this life gives us a way to distribute, to generate values from the uniform discrete distribution. And if we're rolling a dice, right, that would be kind of similar to that, right? In terms of the dice, we could just have 1 plus int rand multiplied by 6, and that would give us the dice. So again, as I said, I hope this is useful, and I feel that especially this last example is clearly applicable to your engineering economic game, and specifically figuring out, how much to bid on the maps, and which type of expeditions to do, what to expect on average, or what kind of return this can give you. All right, thank you, and I'll talk to you soon.